Supposedly, if you listen to this specific song, When I'm 64 by the Beatles, you get younger while doing so. You don't feel younger, no, you actually get younger by listening to that song. Which is a weird research finding, right? So something must be wrong with the thinking or the reasoning behind this type of research, which is what we're going to look at today. We're going to take those critical thinking skills that we, sharpened in the previous block and apply them to psychological research, how it's commonly done, and have a critical perspective on that, whether we should be doing a different way on the basis of what we know and what we will encounter in this block. To give you an example, so the Beatles example, as you know, if you did the readings already, was something that the authors did to make a point, right? Basically saying, well, if I apply model research practices, so the stuff that most researchers are actually doing in the published literature, then I'm able to show that people actually get younger. In a real publication, in a real journal, in a high-impact journal, Gerald Bem, as depicted here, this is the title of the publication, supposedly showed that people would be influenced by primes from the future. So, as I indicated previously, people had to pick a curtain. So either pick the left one, pick the right one, and afterwards they would be shown an image on the left or the right side. And if they picked the curtain behind which was an image, they would have picked the right curtain. And what Bem showed, or he said he showed, was that if he primed people with erotically tinted images, they would more often than not choose the right curtain in 53% of the cases instead of the 50% that you would expect by pure chance, which was sufficient for him to conclude that something weird was in play. Precognition played a role. People were able to sense primes from the future, because what he did was not, as would be usual, prime people before they made the decision. No, he primed them after they picked the curtain, so after they made a decision. So it's a usual priming effect, but somewhat weirder because he offered the primes after he measured the effect of the prime, right? So that's reversing the temporal order. And he didn't conclude, it's weird, I can't understand it. No, he said, no, this must be something beyond the scope of our usual psychological processes, right? Something paranormal must be taking place here, and he called it precognition. Cognitive processes that are influenced by stuff from the future that haven't yet happened. So again, model research practices being used. So this was published in a high-impact journal because the way he went about doing his research and publishing results was very common and very typical for how research was being done, and perhaps in large parts is still being done in psychology. So we have to scratch our heads and wonder, well, what can we believe from the published literature if, using the default research practices, we're able to show such weird results? But there's more. There's a number, which is 96%. And that number indicates the number of publications or research results that actually confirm the expected hypothesis, or so that actually confirm the research hypothesis. So let's say you take a sample out of the published psychology literature and you check to what extent the hypotheses are confirmed. So you test a hypothesis, a statistical hypothesis, a null hypothesis, and let's see to what extent the results of that experiment, that test, were actually positive, in the sense that they confirmed what the researchers expected. And it turns out that 96% of published research in psychology shows these type of positive results. So that means that in 96% of cases, the researchers find results they were actually expecting. That's weird, right? And that's in combination with the stuff about right, and that in combination with the stuff from Feeling the Future, right? Made somebody publish a satire, right? You say, well, Bem proved that people would sense the future and make the right decisions in 53% of the cases. Somebody else said Yeah. That's just 53%. That's peanuts, right? Psychologists doing research, they're able to predict the future in 96% of the time. So that's weird, and we can laugh about that, about this satire, but the underlying result is very serious and very grave, right? So something is wrong if we can use default research practices and prove that, or supposedly prove that weird stuff is the case, that we're influenced by stuff in the future, that we get younger by listening to the Beatles. And while at the same time we know that psychologists are so good in doing research that they can predict the accurate results of their experiments in 96% of the time. If this were actually true, there's no point in doing research, right? You just ask the psychologist, what do you think will happen? And they'd be right in 96% of the cases. So that's how weird the situation is. Finally, and which makes the figure I just showed you, the 96%, even weirder, is that if we try and actually replicate a lot of studies in psychology, then we do see a failure to get those positive results. So in replication studies, a lot of replication studies, we don't see the same results as in the original studies. So we have a situation in which the original studies lead to the expected result in 96% of the cases, but if people try to replicate those results, they have a lot of difficulty in finding the same effect. So something weird is going on for sure. Finally, and to make the scale of the problem even more explicit, in 2015, a large-scale collaboration between multiple labs, so labs of multiple psychologists, took it on themselves to replicate a lot of studies from psychology, to try and replicate 100 studies from psychology. And what you see here is, quite confrontational. So on the left is depicted the p-values from the original studies, which are almost all below the 0.05 criterion that most researchers use, which is in line with that 96% number I just gave you, right? So this just shows that from those 100 studies, most above 90% showed significant results. The replication showed something else. Sure, some of them would have shown significant results as well, but most of them didn't. So most research failed to replicate those significant results. And the same goes for the effect sizes. So even though the effect sizes were estimated to be on average, what would it be, around 35 by 0.35, the effect size estimates, or the effect size that came from the replication studies, was a bit lower, a lot lower actually, and sometimes even in the opposite direction of the original publications. So what we've seen is that if we use default research methods in psychology, we're able to show weird stuff. And perhaps those research practices are then the cause of the interesting fact on one hand that 96% of original studies show significant results, but we are unable to replicate those results in, let's say, 60% of the cases. And the question is, why is that the case? So what is happening here? And that's the focus for this block. What we're going to do this block is give you the tools, or train you to use the tools we've already encountered in the previous block for understanding this situation in psychology. So we're going to look at how people go about conducting the research and reasoning about the results. And we're going to look at, what those model research practices actually are. So what you're going to do is, mainly what you're going to do is learn a lot of statistical tools and statistical techniques, right? So this is an overview of what your next couple of weeks will look like. Each week is a different color. So this week we're going to talk about, today about critical thinking about psychological research, and then you'll start the first of quite a lot of statistics lectures that you will have in this month about the F distribution and running ANOVAs, non-parametric testing, and the next week we'll have statistic lectures about ANCOVA, factorial ANOVAs, repeated and mixed measures, mixed ANOVA, and the chi-square test, and even Bayesian approaches in the final week. The reason for that is that you should be familiar with these techniques. If you're going to the specialization of your bachelor, and especially to your master's, your supervisors there will expect you to be familiar with these techniques, because these are the most common statistical tests that we actually use, particularly when using experimental designs. What we're also going to talk about, and hence my introduction for today, is, a couple of critical footnotes to that way of doing research, that way of running analyses. So today and next week on Tuesday, we're going to talk about how we can use those critical thinking classes that we polished in the first block to look at the way in which people go about doing research and the way in which people reason about statistical inference. And we're going to look at potential alternatives, whether Bayesian statistics is a better way of going about this and a better way of reasoning about your data. That's basically it. And so the weekly assignments are in line with that. The readings are, of course, they're listed here. Oh, by the way, Sharon will have another look at the readings for his lectures, not for the next Thursday, but after that. And he will check whether he can make the references to the reading a bit more specific. So tell you which paragraphs from field you can skip and which you should focus on. But he will do that somewhere this week. One other thing to look out for is that there is an assignment that you need to complete by working together with a group of other students that you know from your tutor group, which is the Good Science, Bad Science assignment. And the deadline for that is on the 16th. And for that, you have to hand in a presentation, a Pecha presentation, and all will be explained in the tutorial. But please bear in mind that it counts towards your final grade. I think it's 10% of your final grade. And in that assignment, you're going to test out, it's going to move a bit beyond just the lecture content, right? So in the lecture, we're going to focus on the main techniques that are being used and the main criticisms that you can target. You can level at those techniques. And in the tutorial, you're going to take a more thorough approach to evaluating research. So what are the different steps that the original authors have taken? Can I train myself in spotting to recognize the decisions they've made and the judgments they've made? And can I train myself in recognizing alternatives? So what could they have done instead, and would it have led to different results or a different conclusion in the end? So that's, of course, what we'll be talking about this week and next week in the critical thinking lectures. And of course, that's also something that will be a factor in the final lecture, which is a debate between two professors on whether we were better off thinking as Bayesians or frequentists. But in the tutorials, there will be a more thorough focus on the actual steps and different checklists that you can use in evaluating research, including your own research, for example, when writing your PTPR report. All right, so any questions about the schedule for this block, for all the things that you need to do the coming month?
It seems like there's more of a focus on statistics instead of critical thinking. Will the same count for the exam as well?
Yeah, so today we're going to talk about that weird stuff, right? So we're able to show weird results using model research practices. So doing the stuff that psychologists usually do, we're able to show that the future influences the past and that you get younger when listening to the Beatles. And we're mainly going to talk about today about how that came to be. And it's useful to differentiate between, the ideal view you might still have about what science is and who scientists actually are, and what real science actually looks like. And we're going to look at questionable research practices, both to have a perspective on why they occur, but also why those practices can be considered questionable. And we're going to talk about different causes and solutions for the state of affairs, with which I mean that low replication rate and that potentially high false positive rate. All right, I see some questions in the Zoom group chat about the exam info. You can find it in the modules. It's way down below, but we still need to update some stuff there as well. So give us the time today to update the exam info, including those percentages those are being mentioned in the Zoom group chat. And then it should be fine by the end of the day. All right, so let's start with the real and ideal science and the difference between them. So what I want you to take to heart, a bit of an ideal perspective, as you will, is on the basis of two quotes by Richard Feynman and one by Daniel Dennett. And I think those are important to bear in mind. So the first principle about being a scientist is that you must not fool yourself, and you are the easiest person to fool. So you have to be very careful about that. After you've not fooled yourself, it's easy not to fool other scientists. You just have to be honest in a conventional way after that. It's a beautiful quote, I think, because you just have to make sure that you don't fool yourself. Don't commit all those biases that people are sensitive to, even scientists. And if you've managed to do all that, then just communicating with your colleagues is the easiest thing in the world, right? You just have to be honest in a conventional way after that. And Feynman expands on that. He's saying, well, I'm not trying to tell you what to do about cheating on your wife, fooling on your girlfriend, stuff like that. We'll leave those problems up to you and your rabbi. I'm talking about a specific extra type of integrity that's not lying, but bending over backwards to show how you may be wrong. So you need to go beyond not lying, right? So being a scientist means being honest, but you have to move beyond just being honest and just not lying, which is bending over backwards to show how you may be wrong. So you have to contort yourself in different ways. You have to go the distance to try and check whether you might be missing stuff, how you might be wrong. And the final quote by Daniel Dennett, makes that final step, checking whether you might be wrong, is a bit easier, because he says that the essence of science is making mistakes in public, making mistakes for all to see in the hopes of getting others to help with the corrections. Hopefully, after today, you know what these three quotes mean and what it means for doing research in psychology, or what it means for doing scientific research in general. It's easy to fool yourself, so you have to do everything in your power to check whether you might be wrong, and you have to do that in all openness, so others can check whether you might be wrong as well, so they can help you with the corrections. So, science is hard work. And it requires critical thinking about your results and the way you go about doing your studies. If you were to peruse the different books that you would find in a popular science section in the bookstore, you know those places, right? You remember them, actual bookstores. It looks a bit easier, right? So if you're doing neuroscience, you can write a book about this is your brain on music, or this is your brain on nature, your brain on food, or your brain on porn, whatever topic you might be interested in. You can write a book about it and just tell people what your brain is doing while you are doing those things, and it makes it look so easy, right? So this is all the stuff we know about all these different topics, but the reality might be more complex, because what you can also show in relationship to neuroscience is that, brain activity in a fish. So if you put a salmon in a fMRI machine and you show the salmon different pictures that are from a set of pictures that are used in research on affect and emotions, right? So those are standardized picture sets of which we know that they would have an emotional response in the people viewing them. But you don't show them to actual human beings, but you show them to a fish in an fMRI machine, and then you try to see what the fish's brain is doing, right? This is the fish's brain on a picture set, an effective picture set. And you can see some activity here, right? So there's some activity here and there in the brain of the fish. Significant activity. But the thing is that fish in the fMRI machine is dead. So that's weird, right? So you're able to show brain activity in the brain of a dead fish. Again, that should make you scratch your head and think, oh, okay. So if we can show these type of significant results even in fish, then in dead fish, then how do we interpret those results? As Ido is saying in the comments, so if it's dead, it won't have brain activity. Yes, that's a very common assumption. And it's either saying that fish can have brain activity, or you have to say, well, the fish probably, since it's dead, doesn't have brain activity, so there must be something wrong in the way I'm doing this analysis. So that's the options you have, right? All right. again, we're talking about weird stuff, right? We're going to show, we already talked about showing that you can become younger when listening to the Beatles. This is part of the study that supposedly shows this. And I've just shown you that you can show brain activity in a fish which is dead if you use those same dubious research practices, which is what we're going to talk about. And by the end of that explanation, you should be able to see and understand what was left out of this research publication. So this is a short description or an abstract from the Beatles study, right? So the song I played at the beginning, When I'm 64, supposedly made people younger in the condition listening to that song compared to a control condition. And you should be able to understand how they were able to show this by trying different things and leaving essential stuff out. So we'll get back to this example after we've talked about those dubious research practices. But basically, my explanation would look like this. So if you want to have a summary of what's going wrong in the way in which people do research, I'm tempted to say it looks something like this. You can look it up yourself if you like the song and you want to see some more of ex-President Obama in action. If I were to ask you after showing you this video, did Obama ever sing Can't Touch This, then you wouldn't be tempted to say yes, he did, right? Because you know, well, this has been edited. A lot of stuff has been left out. So it looks like he's singing the MC Hammer song, but he isn't. Not really, right? So the moral of the story is that if you leave enough out, you can make anything sound amazing. Anything looks true if you can leave out all the details that show it not to be true, right? So if you cut away enough footage of Obama, then you can get this song, get him to sing this song. And in a similar way, if you leave out enough in your research publication, you're able to show that people get younger when listening to When I'm 64. But that's just the general explanation, right? So that's the general gist of what we're going to talk about today, is how do scientists leave out all those parts of the research which are essential for interpreting the results, and why are they doing it, right? And the reason why they're doing this is because research is complex. So this is something I mentioned at the beginning of the course. In this series of test, actually, different research teams were given the exact same data. So they used the same data, and then they had to calculate or do their analysis. So the divergence wasn't in how they set up the research or the questions they were interested in. No, it was just in all the stuff they did after getting the data, because they started with the same data, but even then they got different results, right? So what you can see here is that the gray dots are non-significant results, and the green one are significant results. But even beyond looking at significance, if you just look at the likelihood ratios, and the confidence intervals, there's a difference in sometimes even big differences in what results the different research teams would publish after they've gone through the exact same data. What this shows you is that there's a lot of decisions that you need to make as a researcher. Even if you have the same data, you still have to make a lot of decisions about how you're going about analyzing it. And the fact that people need to make those decisions and do so in different ways, leads to different results, which you might call researchers' degrees of freedom. So the degrees of freedom researchers have in making their own decisions about what to do with the data after they collected it. But not only after they collected it, right? So it's also in just wondering about what you want to do research on, and on what sample you want to use, what hypothesis you want to test, what dependent variables, independent variables you want to use, what measurement procedures, what analysis you want to run, how you want to remove the outliers, if you want to remove the outliers, what you were willing to call an effect, what you were willing to see as a relevant effect given your theory, etc., etc., etc. Those are all decisions that you need to make as a researcher. And that's just the way it is, right? So we can't automate those steps. Perhaps we don't even want to, but that does mean that there's a divergence in what scientists will conclude even on the basis of the same data, because of those researcher degrees of freedom. So, and that's just fine, right? So if we would have ideal scientists, so if the ideal scientist was our best and our greatest rational people, unbiased, super intelligent, fair, very skilled in communicating their stuff, including their mistakes if they make them, but they don't, right? Because it's an ideal scientist, so who makes mistakes? And those ideal scientists would turn the wheel, right, of that empirical cycle, and they go about generating and specifying hypotheses, designing the studies, collecting data, testing the, etc., etc. Then it doesn't matter, right, that they have degrees of freedom, because, I mean, they're all idealized human beings, so leave it up to them to interpret the, well, a situation and make the best decisions. But what we see is that that's not actually the case. So that shouldn't surprise you, right? So if you've done 1 year of studies on psychology, so you shouldn't be surprised that no one is completely rational or unbiased or super intelligent, fair, communicates well at the same time. And we can certainly not expect that to be true in all scientists at the same time. So the question then becomes, how do people go through that empirical cycle, and how do they go about making those decisions given all the researcher degrees of freedom that they have? So this is where one important ingredient of understanding how the situation of failed replications and a lot of false positive findings in psychology might have arisen. So the ideal scenario of the publication process is that you as an author or researcher do your study, you plan it, you design it, you implement it, and you write it up. And then you send your manuscript to an editor, and the editor decides who should review it, who of your peers should do the peer review of that. So the reviewers read the article and they check it for clarity, accuracy, appropriate methodology, theoretical base, and they send it back to the editor, and the editor decides, or the reviewers decide whether it should be published or not, or whether it should just be ignored, or whether it should be revised, right, and resubmit it. So send it back to the author, and the author needs to make changes, perhaps run some extra studies, and then send in the publication again, and perhaps etc. etc. It takes a couple of years, this process, and it almost never happens that it leads to direct. So the reviewers look at it and say, "This is excellent. Publish it as is." It always happens that you need to revise it and resubmit, or that you won't get published at all. But this is the ideal scenario, right? So you do your research, you send it to your peers, they check it on these criteria, and then send it back to you, and you get the results, and you get either published or not on the basis of their review, whether it was accurate and the appropriate methodology and such criteria, whether they apply. But that's the ideal scenario. In reality, it looks like what actually happens is that people do not really check on those criteria. What they actually check, or what they're very sensitive to, is whether the study showed significant results. So this is from a study done by Mahoney back in 1977. So in which papers were sent to reviewers, and the only difference between the papers was whether the results were significant or not. So the paper was the same, but it led to significant results or didn't lead to significant results. And based on only that difference, you can see the differences in the comments that the referees or the reviewers made. So if it led to positive results, they say, "Oh, it's a very fine study. It's an excellent paper." And then they said, well, if it led to non-significant results, they said, "Oh, there's so many problems with this paper. It's difficult to decide where to begin, etc., etc., etc." So at least it seems like people are not checking on accuracy and proper methodology and etc., but just checking, well, does the story check out? People predict something and it occurred or not. And if it doesn't occur, so if significant results fail to materialize, they're more critical about the publication itself. This is another example, somewhat more recent example from the 90s. So one of the researchers quoted here got a rejection letter by the editor, which said, "Unfortunately, we're not able to publish this manuscript. The manuscript is very well written and the study was well documented. Unfortunately, the negative results translate into minimal contribution to the field." And this is rare that it's put that explicitly, right? So they're basically saying all the criteria on which I should check your paper, well, they all checked out. It was a proper study, and it was very well written as well. But the results were negative, so it's not interesting for us to publish it. Which is a big ingredient in trying to explain how it could be the case that 96% of the published research articles lead to positive results, right? Because all the stuff that doesn't lead to positive results won't get published. So we had that ideal scenario, right, of that super intelligent researcher, and now it's time to look at reality of how actual human beings go through that empirical cycle when doing their research. And what we're going to see is that at every step of that empirical cycle, those researcher degrees of freedom lead to, well, choices in people that can be somewhat considered to be dubious. Not necessarily because they want to cheat or want to mislead people. No, because they are tempted to make decisions in a certain way. They're tempted to make those decisions in a way that lead to significant results, because those significant results are more likely to get published, right? So as researchers, those very intelligent human beings have a stake in the matter, right? So they're not neutral in saying it doesn't matter once I've set up my study and run the study. It doesn't matter what happens. No, it does matter what happens, because if you fail to show significant results, your study will fail to get published. And that steers the decision process that we talked about. So the decisions that researchers need to make at every step in the empirical cycle, it steers it, slightly nudges it into the direction of making decisions in such a way that significant results are more likely. So people tend to fail to control for potential bias in generating hypotheses. So they're more focused on confirming their existing ideas than thinking about alternative solutions. In designing a study, they design studies with low statistical power, and they don't think that's an issue because they're completely focused on showing significant results. There's poor quality control in collecting data. So was the measurement procedure in order, or did you take a random sample or not? A lot of p-hacking occurs in the analysis and interpretation of results. And publication bias still adds on that, right? So we have all those steps in the empirical cycle, and we've looked at what an ideal empirical cycle would look like. And now we see depicted in red the potential challenges at those steps, because people are incentivized to get significant results out of their studies. All right. And that, because of those researchers, so we talked about two things, right? So we've seen that the situation is dire. 96% of published research literature shows positive results, but those positive results are very difficult to replicate. And we've seen that might have arisen because researchers at the same time have a lot of degrees of freedom in how they go about analyzing the data, but also that they're incentivized to produce significant results. So now we're going to see, with those existing degrees of freedom, how easy it is to produce significant results. And I hope this link will work. Here we go. Something is happening somewhere. Oh, here. Yeah. So this is from an awesome Popular Science article on 538. You should really check it out. If you feel bummed out by what I'm saying now, and other lectures, perhaps you heard some similar messages about failure to replicate studies, right? So that might bum you out, and might make you even wonder why you started out doing a study about a bachelor study in psychological science in the first place. And reading this article solves a lot of that. Part of the article is this interactive thingy, I don't know how you call it, in which you can hack your way to scientific glory. So, and then there's you're a social scientist with a hunch. I hope you can see this. I'm going to make it somewhat bigger. And basically what you can do is you can do whatever you like with your data set, right? So you can say, well, I'm either a Republican or a Democrat, or I'm interested in results for Republicans or Democrats. And then what I'm interested in is whether the U.S. economy is affected by whether Republicans or Democrats are in office. And so let's say I want to focus on Republicans, right? Republicans are in office at the moment. And then you can choose, right? So am I going to focus when checking out the relationship between the quality of the economy, right? A better economy is on one axis, and the amount of Republicans in office is on another axis. And we're interested in a relationship between the two, the quality of the economy and the amount of Republicans in office. And what we can then do is, well, hack our way to scientific glory. We're looking out for that p-value. And if we just look at senators, as the politicians we're looking at. So on this axis, we're just taking into account senators, but we could take into account more than just the senators. We could include the governors or the presidents and the representatives as well. For the economy, the quality of the economy, we're just measuring by stock prices and inflation, but we could include more as well. And we're almost there. So just starting out, we're at the P value of 0.08, right? So we've almost hacked our way to scientific glory, but we're not quite there yet because our results won't get published if we leave it as is. So let's see what happens, right? So if we include, oh, there we are. So if I not just use the data on senators, but also do the representatives, then I have a significant correlations between more Republicans in office means that the economy is doing somewhat better. But let's say I'm not a Republican, my inclination is more towards the Democratic Party, then this would be disagreeing with my political views. That's not something I would like to see confirmed when doing research. So, well, let's take out the representatives and include the governors. Let's see what happens. And the president, no, that just doesn't look right yet. No. But you see what I'm doing, right? So, oh, okay, here we go. If I just include presidents, I'm getting a significant... no, it's not. Yeah, I'm getting a significant negative correlation. So I'm able to show that if I look at the more Republicans are in office, the worse the economy is doing. Or I can show the inverse, right? Whatever I want. Or I can show non-significant results by choosing what to include and what to exclude from my analysis. So what I'm trying to show here is that basically those researchers' degrees of freedom in combination with a motivation to show significant results and perhaps your political inclinations as well, your existing worldviews, well, might make for a data set that's a bit like a horoscope, right? So you can see whatever you like in it, and depending on what you leave out and what you decide to leave in. So the question then is, how common is this, right? So I can show you this graphic, and that all looks fine indeed with this data set, but how many researchers are actually engaging in these practices that might lead to these, non-representative results? Quite a lot, actually. So if you just look at the self-admission rate from a study in 2012, a survey done in 2012, then you can see that 78% of respondents fail to report all dependent measures, and 72% continue collecting data after seeing whether the results were significant, and if they weren't significant, they continue on collecting data. 67% admits to selectively reporting studies that worked. Well, that's not 67%, by the way. The 67% is the prevalence estimate. So what we can see is there's a couple of questionable research practices, and I think there's reason to believe that a lot of researchers are actually